any questions about the course, and I think there's a couple open questions that I wanted to answer with the recording on, so that everyone will see it, right? Any questions? Yes.
What is the format of quiz?
Okay, that's a great question. So what is the format of the quiz? So you're going to see something like this. And this is probably a screenshot from one of the previous quizzes. So we're going to give you a link, and then you're going to go to that page, and each one is going to be a multiple choice question, and you actually have multiple shots. Okay, so you can the point is not to kill you. Okay, the point is that you have multiple opportunities to answer the question until you really understand. Okay, so that's the format. Okay, any other questions? How about RIDE? Does anyone still have problem with using RIDE at this point? Any authentication problem? And so what is the problem now? The credentials?
Yeah.
Okay. So send the email to me and to Andy Shu, ASCHUH. At Illinois. Okay, and so copy me. Then you should have received the credential. Are you registered late, or you're?
Like the day before the class.
Okay, so that he probably missed your, when he wrote, what he does is that he rolls up the class roster, and then he sends out all the credentials. So he probably missed your a couple ones. Okay, so we'll get it done. Okay. Yes.
So how do we submit the lab? Like when we are done with the lab, just running the RIDE automatically submits it? Or?
Yep.
Right.
Yeah. And it will be recorded. Yep.
Right.
Okay. So any other questions? Yes.
Deadlines for labs.
What's that?
Deadlines for lab.
Oh yes. So our tradition is on Thursday. So the first lab should be done due this coming Thursday. Okay. And to try to plan accordingly, and we'll also release the labs early, so that if you need to go interview and so on, you can work on the labs early. Okay.
What time?
What time? What time do you want?
I'm fine.
11 p.m. Would that be okay? Right? Okay. Anything else? Yes.
The first lab, you mean the device query or the scatter?
No, that's lab 0. So it's the scattered again. It shouldn't take that long. So if you give it a good couple hours, you should be able to just do it. Okay. And it will become a little bit harder, but we'll give you more time when the labs become more difficult. Okay. Try to keep up. Try not to fall behind. If you just keep up with this class, it should be a very, I would say, it should be a bit quite enjoyable. The lab is designed in a way that you should be able to spend reasonable amount of time, and then you will have some good experience. Okay, so make sure that you don't fall behind. How many of you have taken 408? And yeah, you know the style, right? These things are not like super time consuming, but if you just keep up with the course, you should be fine. Okay. So we're going to start. The second topic, which is thread coarsening and register tiling. This is a somewhat, I would say, quite intuitive subject, but it actually could, but most people don't really understand, the details. So, the point of this lecture is for me to talk about two important use case examples to show you the details involved in thread coarsening and register tiling. So the idea, the objective here is for you to learn about these two very closely related techniques, and these techniques really trade parallelism for more efficiency in memory accesses and more efficiency in compute. Okay, and especially it's important when the application is memory bound or compute bound. So when we parallelize an application, the first question is, do we have enough parallelism? If we don't have enough parallelism, if we have a lot of sequential sections, we're going to be out of luck. But when we are successful in parallelizing these applications, we get lots of parallelism, then we start to be bounded by something. Okay? Sometimes it's because we're accessing too much memory, and then for 408, you saw that the memory access could be the bounding factor, so you will be memory bound, right? So if you can eliminate some of the memory accesses, if you can do more coalescing of the memory accesses, then you start to get performance. And in some cases, you could even be compute bound. You could have applications where the compute is actually saturating all the execution units. And that's a very good situation, but if you can make things more efficient, you can actually further improve the performance. In some machine learning situations, you can actually be in compute bound, right? So that's why we have these two techniques that combined together can often improve the efficiency, so that when we have a very, very polar application, we can further improve the performance by eliminating some of the bounding factors, right, of our speed. So thread coarsening is a very, very simple, conceptually it's extremely simple. We have all these threads, and the threads are are doing some kind of computation and doing some memory accesses. So we start with having certain amount of work we assign to each thread, right? In 408, you saw the various techniques in terms of associating the work with the block index and thread index, right? That's how we assign work into these threads. Now, sometimes these parallel execution require, doing some redundant work. So, for example, when we come into CUDA kernels, oftentimes the kernel at the beginning will do some work that is common to all the threads, and then you specialize into the execution of threads. So here I'm showing a sort of a conceptual illustration where we have these threads that will execute over time. And so these are 4 threads, and then after you enter the kernel, the threads will be doing some kind of common, redundant work. So, for example, calculating the thread index and thread, block index, right? Doing some preparation work, and then each thread will be doing some thread-specific work. So these are the unique work that each thread will be doing, and then sometimes you need to finish by doing a little bit of redundant work among all the threads, so that you can finish up the execution. So here I'm showing one thread, and then the hardware is going to move to the other thread, and then hardware will move to another thread. So over time, we're going to have the execution of these threads, and then every thread is going to do some redundant work and some unique work. When we have enough parallelism, and we can afford to sacrifice some parallelism and improve so that we can improve performance, what we can do is we can fold multiple of these threads into those work into one thread. So here we merge 2 of the threads into we merge these threads into 4 threads into one execution. So essentially, what we can do is we can actually use fewer threads, and then we still need to do that redundant work. But that redundant work now need to be done only for processing 4 data elements rather than processing each data element. So we do a little bit of redundant work. We do we do this work here, and then we do all the 4 all these 4 other the unique work that are folded or multiple of these work folded into this. So essentially here we're showing 6 threads worth of work rather than 4 into each thread, so that we can actually get some efficiency. So now if we amortize the unique work, the redundant work by the 6 data elements, then on average we're doing a lot less redundant work. So this is conceptual, okay? So let's begin to look into the specifics, because conceptual is simple, but until the tire hits the road, you don't see some of the specific challenges. So the outline is we merge multiple threads so that each resulting thread calculates multiple output elements. Instead of calculating one output element, we have each thread to calculate multiple output elements. And we perform the redundant work once and save the result into registers, and then we use register contents for calculating all the output elements so that we don't have to repeat that calculation for all the output elements. Okay? And the merge kernel code will use more registers. So this is the cost. Because essentially what we're doing is we're doing the redundant calculation only once, and then we save it in a register. The register is easy to access, it's fast, but then the register consumes a critical resource, right? The register file is a critical resource in the GPU, and in fact in any of these machines today. So you all know that about the occupancy, right? So if we start to use up too much of the resources, the number of thread and thread blocks that we can accommodate in each of these streaming multiprocessors will be reduced. And if some of these things don't make sense, we have the prerequisite material in the website. So go and look at some of the EC 408 lectures, and you can catch up very, very quickly. So if we use up too many registers, we may reduce the number of threads allowed on each streaming multiprocessor. And so increased efficiency in this case may still outweigh the reduced parallelism, especially if ample parallelism exists for that given hardware. So there are two things here in play. Okay, when we say reduce parallelism, there's something very obvious. The obvious one is we reduce the number of threads, right? Because we fold multiple output elements into one thread, we're reducing the number of threads we're generating. So that's one level of reduced parallelism. Make sense? That's the intuitive one. The less intuitive one is because now we're using more registers. So the number of threads that can be actually assigned into the streaming multiprocessor at the same time, this is the hardware level, could also reduce. So we could have double factors, right, in terms of reduced parallelism that's actually used at runtime. On the other hand, if we improve the efficiency enough, and then if the code is actually being memory bound or compute bound, then we can actually come out ahead. In many cases, we actually come out ahead in a very significant way. Okay? So the section in the third edition is section 5.5, and then if you take a look at the textbook chapter, you will see some a little bit more elaboration on this. So we're going to first start with thread coarsening and register tiling for the ECS kernel. This is the kernel that Carl went through last time when we did the scatter together transformation. Right? The scatter together transformation is extremely powerful because it takes the conflicts and takes these conflicting writes away, so that essentially you do a owner compute assignment to the threads, and so these threads no longer need to do the atomic operation with each other, and each thread is going to be just collecting the input, right? Collecting the input for that particular output, and you can use the collective caching and the collective memory coalescing and so on to be able to collect those information very quickly. So that's why for GPU programming, scatter together is extremely powerful because it eliminates the serialization from the atomic operations and also make the memory use system much more efficient. For MPI kind of programming, scatter together essentially gives you owner compute rules so that you can minimize any of the global the MPI collective that you need to implement in order to generate the result. So that also can dramatically improve the performance. So that's why it's one of the the most essential technique that you need to think about. In fact, one of my students, that did a summer internship, in fact, Mert is here, right? Mert, yeah. So, the first thing he did with Argon was, gather to scatter, right? And so one of the very first things you guys had to do to get that software to be scalable. That was at my MPI level. So, for the direct Coulombic summation kernel, after you have done the scatter to gather transformation, now you have plenty of parallelism, and you don't need to have atomic operation. But then we do have some level of redundant work across these across these threads. So we can perform thread coarsening and register tiling by merging threads to calculate more than one energy grid point per thread. The way that we talk about it so far in that energy calculation is that every thread is going to be calculating one grid point potential, right? The potential at one grid point by summarizing the effect of all the atoms, right, on that particular grid point. And so, if we merge multiple grid points work into one thread, then we can actually achieve. We'll have two effects. One is we will result in a bigger computational tiles. So this is where one of the important challenges of thread coarsening actually start to happen. Okay, we can talk about abstract all day long, but as soon as you start to look at real applications, you will start to see some real challenges. The first one is the thread count per block may need to be decreased in order to control the computational tile size. Remember, we were using a thread block to calculate a tile of output grid points. So if we start to increase the number of grid points calculated by each thread, but we keep the number of threads the same, we're increasing the number of grid points covered by each thread block, right? We keep the thread number the same, we have each thread to calculate more grid points, then the thread block will be covering more data. So the data tiles will begin to increase. So this is one important thing that we're going to go over. And so we may need to reduce the number of threads in each thread block in order to be able to control that tile size. So why do you need to control the tile size? We're going to get into some of the side effects. The other one is that so otherwise it gets bigger, and so the threads do more than one lattice point calculation, resulting in a significant increase in padding and wasted computation at the edges. So this is illustrated here. Let's say we have this is our data grid. Okay. So the data grid in this case is 5 by 10. Okay, 5 vertical and 10 horizontal. And let's say we have a thread block, each thread block to cover 8 grid points, right? So we use 8 threads, 2 threads in the vertical and 4 threads in the horizontal to cover 8 grid points each. So when we generate the thread blocks in CUDA kernel launch, we're going to divide the number of grid points by the number of grid points we cover in each thread block, right? So horizontally, we need to have 3 thread blocks in order to cover all the 10, but then we will have a couple of threads that are going to be wasted, right? These are the additional threads that will be turned off, right? So that's what we call the idle threads. They're not going to be participating in the execution. They will add to the divergence, right? And so that's these are the what we call the the idle threads in terms of the idle threads in terms of the boundary thread blocks. And in terms of memory access, oftentimes we actually need to pad our data grid to include 2 more grid points here because of memory alignment problems. So essentially, when we have a data grid of this size, and then we are partitioning all these data points into thread blocks, if we didn't have any padding, if the data structure is exactly like this, remember the data actually gets laid out in the memory system with row major layout. So this data point here is actually immediately after this guy, right? And this one is immediately after this one. So in the memory system, you're going to have, these things are actually going to start in some kind of funny location, okay, in the access. So most of the memory systems don't like it when you have all the threads accessing in a non-aligned access pattern. So that's why oftentimes we need to, we ended up padding additional points so that we guarantee that the next one starts at a nice boundary, which is usually 64-byte boundary of the access, okay? So this involves a little bit of padding, for high performance code, and also involve two threads that will not be activated. In the code, you will see that if the thread ID is greater than something, you turn it off, right? Okay, so any question about that? Okay, so let's say if we do a simple thread coarsening by assigning, 2 grid points to each thread. So now each thread processes 2 grid points. We still have the 2x4. Okay, we still have the 2x4 block size. So we still have 8 threads in the thread block. But every thread is going to process 2 grid points. So that means that in the x direction, in the x direction. So that means that in the x dimension, now every thread block is going to process 8 data points, right? 8 data points. And the horizontal direction is still 2, right? So this is what we call the dimensional thread coarsening. We coarsen the threads in the x dimension, but not the y dimension. So this essentially gives us a bigger data grid coverage for every thread block. However, we start to have a kind of an exaggerated quantization effect at the boundary. Now you see that instead of having 2 extra points in the x dimension, we actually now have 6 extra points in the boundary connection, right? So we will have more threads deactivated, right? Deactivated in the boundary, right? So we have more wasted threads. And in order for the accesses to be aligned, we still need to have this padding, and then we most likely will require more padding at the end in order to be able to do this. So this is a very typical situation in a lot of the rendering software, in a lot of these the molecular dynamics software, in a lot of the even the fluid dynamic software. When they have these grid concepts, when we do the thread coarsening, we oftentimes need to factor in the cost for this. And then, we can mitigate this by reducing the number of threads in each block in the x dimension. So instead of doing this, we were going to have the next slide where we are having every thread to process 2 data points. Okay, but we reduce the number of threads in the x dimension from 4 to 2 in the thread block. So we actually reduce the thread block size, okay, and only have 2 threads in the x dimension. So then altogether, these 2 threads are covering exactly the same same number of data points as the 4 threads before thread coarsening. So that the effect on coveraging the data tile remains the same. It doesn't have to be always the same. It's just that when you coarsen in a big enough factor, sometimes you dial it back and reduce the number of threads by 2 or something to mitigate the effect of these enlarged thread blocks. Okay, does that make sense? Enlarged data tiles. Make sense? Okay. So we keep the data tile size the same in this case, and then reducing the number of idle threads, because in this case we will be able to reduce the number of idling threads as well. right? So that's the kind of the point. So here, let's, someone was asking about quiz, right? So a typical quiz question for this kind of thing is that, we can say, assume that we have a 1,000 by 1,000 energy grid, okay? So 1,000 points by 1,000 points energy grid. And we have 16 by 16 thread blocks. So how many thread blocks are there without thread coarsening? So if we have every thread to cover one energy grid point, how many thread blocks are we going to have? It's actually, this is not a trick question, okay? This is a very simple question. So you divide 1,000 by 16, and you take the ceiling of that. That is, you ramp up to the next one to make sure that you have enough thread blocks, right? And then you also take 1,000 divided by 16. So the next multiple of 16 after 1,000 is 1,008, right? So you will have 63 thread blocks in X dimension and 63 thread blocks in the Z in the Y dimension. So we have 63 by 63 blocks. And if we have let's say 4 grid points per thread, then then we are assigning multiples of 16 in the X dimension, right? Multiple of 16s in the X dimension. So we need to make sure that the X dimension is multiple of 16 rather than multiple of 64 versus 16 now. So the next multiple of 64 after 1,000 is 1,024. So this is the increased the block size and increased padding that we're going to have. So we're going to need to have 24 additional elements rather than 8 additional elements in our padding and so on. So this gives us 1,024 divided by 64. So we are going to generate 16 thread blocks. We're actually generating fewer thread blocks. Okay, we're generating fewer thread blocks. However, we're covering a bigger data grid, and that data grid would incur padding costs and wasted thread costs. Okay, so because we didn't coarsen in the Y dimension, so the Y dimension is still just 16 thread blocks. So the total number of thread blocks after coarsening is going to be 16 and times still 63. So 16 times 63. So this is not coarsen dimension. This is coarsen dimension. Make sense?
Yes.
Okay. Any questions about that? Okay. So now we talk about coarsening. Okay. Coarsening is relatively simple as long as you pay attention to some of the side effects. Okay, side effects when you process data grids and so on. So then you're okay. But coarsening by itself doesn't really improve efficiency unless you start to take advantage of the intermediate data or memory data in the registers, so that you can avoid doing the calculation for redoing the calculation for multiple of these grid points. So that brings us to register tiling. The registers are extremely fast. Okay. In GPUs, registers are much faster than the memory system. But for those of you who really understand the hardware design, the register file design is actually somewhat similar to the shared memory design. Okay, in terms of the hardware structure. So, in terms of hardware, it does not necessarily have very, I would say, dramatic improvement in terms of latency. Okay, over, let's say, shared memory. Okay, there's not a dramatic difference at that level. However, registers are accessed through the register numbers in the instruction, whereas shared memory is still being accessed as a memory location. You need to have a memory access instruction to access the shared memory. So you actually need to have additional instruction in your instructions execution pipeline in order to get the data out of the shared memory. Okay, so that's why the register file is can be accessed with fewer instructions and still faster in terms of the total latency, because you reduce one instruction latency for accessing that data. Make sense? So, but the problem with registers is that these registers are private to each thread. Whenever a register is associated with a thread, that register can only be visible in terms of read and write by that thread. The other threads cannot see that value. Okay, and whereas shared memory is visible to all the threads in the same thread block. Okay, so the threads cannot share these computation results or load the memory data through registers. Only one thread can see that register content. So with thread coarsening, remember we folded multiple data elements into one thread. So we used to have multiple threads doing the computation, right? Each one is doing that redundant computation. But if we only have one thread doing the computation, now we can just do that work once, save it in the registers. And the same thread, when processing these other data elements, can now use the data. If we didn't do the thread coarsening, then the work will be, the calculation of different data grid points will be done by different threads. In that case, the threads cannot benefit from each other's temporary results, right? So that's the reason why these two are so closely related. But without thread coarsening, you cannot take advantage of registers. But without register tiling, the coarsening itself doesn't give you much benefit. Okay. So with thread coarsening, the computation of merged threads cannot share the registers. So in practice, what does that mean? So let's go back to the DCS kernel and look at how how the register tiling can provide benefit. So so when we add each atom's contribution to several lattice points, let's say the thread we're going to be adding the effect of this atom to these multiple of these grid points. And we need to calculate what? We need to calculate the distance, right? Because the contribution of electrical charge to the potential is inversely proportional to the distance. So we need to calculate for each grid point, we need to divide the charge of the atom by the distance from between the atom and that grid point. So the calculation of that distance involves the x component, the y component, the z component, right? It's and then the square root, right? So it's the partition, the typical partition distance calculation. So so when we do each calculation, the potential of A and potential B and so on are going to be each divided by the distance from A to the atom, from B to the atom, and so on. So that's fairly simple. So when we look at the energy grid, what we typically will have, when we do the thread coarsening, we're going to have every thread to calculate multiple grid points. But the way that we do the assignment is not to assign multiple consecutive grid points to each thread, because we need to we do have memory correlation. So what we do is we assign the neighboring grid points to neighboring threads, so that when they read the grid point value, write the grid point value, they will be coalesced. However, we assign the multiple grid points that are non-consecutive, so that when all the threads finish with these, let's say these grid points, they all move to the next group, and they all move to the next group. So the grid points that we assign to each thread is going to be non-consecutive. Okay, and this is purely because of GPU idiosyncrasy. Okay, this has for CPU, you actually will do the other way around. You will assign consecutive grid points to the same thread when you do the thread coarsening on it. Let's say x86 or PowerPC kind of architecture. So threads compute multiple potential points. skipping by half warp. So in this case, it's 16 because of the minimum of 16 for memory coalescing. So let's say if we're going to show you a kernel that processes up to 4 lattice points at a point in the inner loop. So every thread is going to process 4 lattice points, and so the subsequent lattice points computed by each thread are offset by at least half warp, for coalescing, and the loads and updates, and updates 4 potential lattice points from global memory at the completion of the summary. So basically, every thread is going to be loading and updating the lattice points, at the end of the kernel execution for operates. So this is kind of the example code. So this is a gather code because every thread is going to be calculating the grid points, and by collecting the effect of the atoms. That's why all the threads are iterating through the atoms. They're collecting the effect on behalf of the grid points. So this is gather code. And here is the important savings that you can get out of thread coarsening. All these points are going to, all the points, multiple points to be calculated by each thread is going to be in the x dimension, right? In the x dimension. What that means is all these grid points will have the same z coordinate and the same y coordinate, right? So we can just take, so for this y coordinate, we can just calculate it once. We can take the common y coordinate, the coordinate of the grid points, and subtract it by the y coordinate of the atom, right? The atom and the common y coordinate of all the grid points. So we don't need to calculate that y delta square for the distance for all the grid points. They all have the same values, right? So this is, this savings in compute, right? So this is what I mean by the redundant work, because all these, when they used to be calculated by different threads, each thread is going to be calculating that y delta and do the square redundantly. Now that you folded the value into the same thread, you no longer need to do that multiple times. You only need to do it once, and you assign that to this funny variable called dy squared product z squared. Because for this code, an implicit assumption is that all the grid points that you pass into a kernel have exactly the same z value. Everyone has the same z value because you're passing a plane to the kernel. So you don't even need to calculate the z delta once. You can just pre-calculate the d, the d value, right? And then you just store it. So this is that information. And now for dx, all these 4 points the thread is responsible for, they will have different x coordinates. The grid points, right? The 4 grid points will have different x coordinates. So that's why you need to do the subtraction, right? The subtraction of the grid point x value and the atom's x coordinate, right? So you need to do the subtraction separately, and then when you calculate the actual contribution, you need to have these unique portions that you take the square, you do the total, you add up the total sum of squares, and then you do a square root, right? So the only thing that you save is this part. So this is the register tiling part, right? You're using an extra register so that you can save this value for all the subsequent computations. Now, this, even though we wrote it this way, the compiler is going to only fetch the atomic charge value once, and then it will be used for the calculation of all these expressions. So this allows you to only access the memory once for the atom charge value, And then you can use that for all the calculations. So then this is how the memory efficiency, right? This is the memory, how the memory efficiency gets improved. This is how the compute efficiency gets improved. And so we're using one extra register for this thing. We have, one extra register for, for this component. And also, remember, because we're calculating multiple grid points, each of these now occupy one register. So in the original code, you only need to have one data point, right? One grid point. So that's only one register. Now you need to maintain 4 registers, right, across the kernel lifetime. So these are the factors that increase the register usage, across the kernel execution lifetime, right, the thread lifetime. Yes?
I just had an idea. So because we're dealing with floats, right? But we're dealing with grid, which is like uniformly distributed.
Yeah.
Could that help if we round that up to like integer and use, for example, integer 16 or something?
Yes.
To buy some memory and like more fast computation.
Absolutely. So the question is that conceptually you have the grid index.
Yes.
The grid index is going to be integer,
Yeah.
but you have the physical distance concept, which is floating point. And there is a what we call the grid spacing. So if you look at the code, you will see that grid spacing in lecture 2. So that's how we multiply the grid index so that we get the real distance, right? So you can potentially do this, especially if you can use a smaller integer, for some of the calculation. However, until recently, you're not going to get much out of it because the integers, you really don't have in GPUs anything less than 32-bit, is actually was not very efficient. You actually the compiler will do the casting and then casting back. So if you try to use a 16-bit integer, okay. However, starting with the Volta generation, now we have native 16-bit integer. In fact, I think it's the next one to Turing. Starting Turing, you have the native 16-bit integer calculation. So it is something that you can begin to think about. So this is a very, very good question. As the hardware improves and as the hardware becomes more and more capable, the best algorithms evolve. Okay, there's no question about that. So it's definitely worth thinking about. So come and talk to me about it. We actually have a couple of Turings, right, in our lab. So something to think about. So there's some pros and cons about these Coarsening kernels, and I already mentioned this. So just want to kind of summarize it one more time, and then we move on to the next use case, which also show you some additional complexities and benefits. So we can reduce the number of loads by reusing the atom coordinate, right, and the charge values, right. So we do that. We save them in the registers for multiple of these grid points, or what we call the voxels, in the domain terminology, by storing them in the registers. So by merging multiple points into each thread, we can compute this thing, right? The delta y squared and delta z squared only once across all these data grid points, and use them multiple times, reducing the compute. And so a good balance between the efficiency, locality, and parallelism, can be done this way. And one thing that I also want to make sure that you understand is that GPUs are not magic. Okay, I just came back from Silicon Valley. Okay, 10 years ago, when I talk about GPUs, people will say, "Oh, those are toys, and then they'll never be used, and so on." And I said, no, guys, look, they are real hardware. Okay, there are some applications that can really benefit from this. So that was 10 years ago. This time, when I go to Silicon Valley, everybody's like, "Oh, GPUs are magic. They can generate billions of dollars automatically. So anything can execute on GPU." I said, no, guys, not that. Okay, GPUs are real hardware, and there's some applications that will run well, and you need to understand some of the limitations. Take my class, okay? And then you'll come to Illinois, learn. Okay, so that's kind of I'm being recorded. Okay, so So the point is that square and square root are done as by special hardware. They're not exactly the same as simple floating point add and floating point multiplication. They're actually being done by what we call the special function units. And these special function units actually have lower throughput, okay, and longer latency. So when you reduce some of these square and some of these square root kind of things, you can actually have disproportional improvement in your execution, not because of latency, it's actually because you have much higher throughput, okay, compared to doing those square root operations. Okay. So now the cons for this approach is that you use more registers, and so this is one of the several limited resources, and you can increase the effective file size and decrease the thread count, active threads in the boundary blocks. So any questions about thread coarsening in the particular, in this particular use case? Yes.
Like if you want to keep on coarsening and using more registers, and when they get finished, like so you use the global memory, then
Yeah. So essentially, what happens? So the question is, what happens when you just keep increasing the use of registers? What happens is that at some point the compiler can no longer map the variables into registers, so that it will start to spill. And spill is typically done into the global memory. So you end up generating a lot of global memory in the back when you think that you're using registers. So you start to see a performance impact. Okay? So one of the very, very important use case for thread coarsening and register tiling is actually stencil computation. It's a little bit different from the molecular dynamics application, some of these gridded potential calculation. So, and this is something that is widely used in all the differential equation solvers. So that's why this particular use case is very important to understand, not only for GPU programming but also for NPR level programming. So I'm going to walk you through the use of thread coarsening and register tiling for solving these kind of stencil denseless stencils. So the stencil computation describes a class of nearest neighbor computation on structured grids, and it's the official sort of domain name for this is Jacobi iterative method. So basically, you're solving a differential equation, and then you're taking the iterative approach to approximate the solution. And then during each iteration, each point in the grid is updated with a weighted linear combination of subset of neighboring values and itself. So the optimizations and concepts, covered by these methods, improving locality and data reuse, and 2D tiling in shared memory, and then coarsening and register tiling. So we're going to walk through a really high performance algorithm for solving stencil on the GPUs. Okay, so that would give you a couple more dimensions of how people really use thread coarsening and register tiling in practice. So basically, for every data point, you're going to have you're going to be calculating the next value for the data point using the data point itself and surrounding data points. There are a few terminology that I wanted to just make sure that since this is a graduate level class, I'm going to give you a little more terminology so that when you read the literature, it will make sense. One is the order. Okay, the order of the stencil. So the order of the stencil means that the number of points in each dimension that you're going to be using. So here we're seeing a very, very small stencil where you're just using the X, Y, Z neighbors in yourself. So this is what we call the 7-point stencil, right? 2 points in each dimension, 6, plus yourself, 7. And you can easily have, something like a 25-point stencil. So the 25-point stencil means that you're using 3 points in each direction of the axis. Okay, so 3 in this direction, 3 in this direction. So that gives you 6 in each coordinate axis, right? Then you have x, y, z, right? So that's 19. Sorry, that's 19 points. So you have 6 in each axis. So that's 18 total plus itself. So that becomes the 19-point stencil. You can also have more complex stencils, such as some of the stencils, because you can imagine when the data points start to go out in these directions, the points that are in between axes will become important in a numerical sense. Because if you include some of these points far away from you on the axis, why don't you include the points that are close to you in the, let's say, in the diagonals, right? So there are even bigger stencils that will use the diagonals between the axes, and that gives you even more computational intensive, more intense computation when you update each point. Okay, so the higher order stencils, and also the stencils that require you to use the non-axis points. So these all add to the register pressure. These all add to the memory accesses and compute of these of these methods. Okay, so real PDE solvers oftentimes use each side numerical. So you could use 24, for example. So that will be the 4 on each side. So 19, 24, or even more, right? So 4 on each side is 8 per axis. 24, for the three dimensions plus itself. So that's 25. Okay. Now, so there are a few things about stencil computation that are important to know. One is high degree of parallelism. The way that we update the grid point, all these points, all these stencil grid points, is that we use the neighbors and its own value, right? So we do a whole lot of computation, we just write into one of the points, and the writing of these grid points are independent of each other, right? So it's an extremely parallel process. They're just for big stencil, for big grids, these things can be extremely parallel, but it's very intensive. Updating each point requires reading many points, right? For 25 point stencil, you need to do 25 memory reads in order to update one grid point. And so many reads for each data point, and it will be nice for us to reuse that data, right? For us to not to have to access memory for every of these data points. If the neighboring threads use the same data points, let's try to reduce the memory accesses, right? And low computation intensity. So every time we read from memory, we're only doing a multiplication or just a simple addition. Okay, so that's why if we don't reduce the memory accesses, since we have very low compute intensity, we're not going to have much advantage from the GPUs. We're going to be memory bound, right? We're going to just be limited by the memory bandwidth. So the base case is that each thread calculates 1 point, and the challenge is how do we exploit parallelism without reusing, without over subscribing to or using the memory bandwidth. So let's take a look at the kind of the reality of these memory accesses. So let's say this is a 7-point stencil. Okay, so the output value of ijk of that grid point depends on the input of that grid point, and then the six neighboring elements on the axis, right? So that's why you have I minus 1 and I plus 1, right? J minus 1, J plus 1. K minus 1, K plus 1, right? So those are the 6 neighbors, right? Plus, minus, plus, minus, plus, minus. And the way that we do the numerical approximation is we add up all these values and multiply by by C1, which is actually 1/6. So this is the second order differentiation. If you take a look at the Taylor series expansion for solving these numerical analysis. So that's C3 is -6 and C1 is 1. Essentially, it's 1 and 1/6. Okay, so that's effectively what it is. And then you will write the out array. So when we actually look at the memory layout for these elements, let's say if you have a center element IJK, the X neighbors are truly neighbors because we have row major layout. So these two are the X neighbors. Okay, so the I minus 1 comes here, right? And I plus 1 is here. So these are the real neighbors. And then the J neighbors are not really neighbors. The J neighbors are in different rows. So this is the previous row, and this is the next row, right? And then the Z neighbors are even farther away, right? This is the next plane, and this is the previous plane, and this is the next plane, right? So these are the data elements that you're going to be accessing, in order to update this, right? So that's the memory, kind of the memory layout view. So the first thing that we can do is to say that, look, if I look at the calculation of the values for the vertical neighboring grid points, the vertical neighboring, right? They're z plus 1 away from right? They're 1 away in the z coordinate, right? So if I look at these values, they will be, the calculation of these grid points actually use some common, right? Some common input values. Because remember, we're using, for each grid point, we're using the up neighbor and down neighbor for the z, right? So when we calculate, let's say this guy, we're going to use itself, the one above it and the one below it, right? And then when we calculate this one, we're using itself, one above it, one below it. So the one's upper neighbor is exactly the cell itself for the upper neighbor, right? So we will have some overlapping input usage when we calculate these vertically neighboring elements, right? So this leads to a very commonly used technique called input queues. Okay, we use registers to maintain an input queue, and we start by, let's say, we have an iteration here, and then if we move to the next one, the current, the one above, the one below becomes the current here. The one above actually is the previous current, right? So if we maintain the 3 input elements, when we move to the next vertical output, we only need to fetch 1 new element. We don't need to fetch 3 input elements, right? So by maintaining a queue like this, we effectively only need to fetch 1 new value, right, out of the 3 used in the z dimension. And so you see this kind of technique again and again in a lot of the applications. Whenever you traverse through some kind of dense data structure, okay, maintaining that queue is is one of the most commonly used techniques. So here is what we do. We think about this. You can do it either direction. So let's think about it as a traversing up from the bottom. So every thread, instead of processing just one output, okay, one output grid value, we're going to traverse up in the z dimension and have that thread to calculate every grid point along this trajectory. Okay. And so if we would do the iteration from bottom to up. Okay. And each block computes so every thread now computes what we call the thin pencil. Okay. This is the tip of the pencil. So you calculate a thin pencil of grid points, right? And in a lot of the NPI applications, when you will see the term pencil for exactly this reason. Okay, they're calculating for each MPI rank will be calculating multiple of these values along one of the dimensions. So this is a thin pencil, and then if you look at the thread block, so the thread block will be calculating for will be calculating some kind of a two-dimensional collection of grid points, and then they all move to the next one. They all move to the next one. So if you look at the trajectory of the entire thread block, right, all the threads in the thread block, each of them is calculating what we call a column, right? It looks like the column of the building, right, that consists of all these pencils, right? So that's a column of the calculation. So the base case is that each thread will load all its input elements for an output from the global memory independent of other threads. So the dumbest approach that we can have is that all the threads are traveling up, right? They're traveling up. And every time you do a calculation, you take, so essentially you see at the output point, you go up, you go to the right, you go to the left, you go to front, you go back, and fetch all the 6 elements. And then you do the calculation for that data. And every thread will do it independently. So that will require 7 memory accesses to calculate every output point. That's the base, okay? But you can do much, much better than that. So the first one is this cube thing. Because we're traveling up, and we're calculating multiple, each thread is calculating multiple grid points. So at any particular time, we're going to be, let's say, calculating this particular grid point. Then, the point that's below it is the bottom. The point that's after it is going to be the top, right? So we're going to calculate this point based on this guy, and then 4 more points in the horizontal plane, right? So we can say, well, we don't need to access 3 data points as I just already outlined before. For every time we start with the bottom, so we fetch 3 points to start, and then when we move up by 1 point, the current becomes the bottom, the top becomes the current, and then you just fetch 1 new item. You just fetch this 1 new item as the new top, right? So on average, in a vertical direction, I'm only going to be accessing doing 1 memory access per each additional grid point that I access. And this is the register tile. And this tile is a little bit different than the tile that I talked about in the DCS kernel. This is a queue tile. Okay, this is a queue tile that you will keep rotating through the register. So the savings of this coarsening kernel is that let's assume no data reuse along the z direction. You have 7 accesses. With the data reuse, now you only need to load 5 for each data element. Initially, you need to load 3, but then every additional one, you only need to load 1 more in the z dimension, and still 4 in the horizontal surrounding points. So now you have, on average, 5 per data point output data, right? So you eliminated 2 of the 7 memory accesses on average, for calculating your grid points. Any questions? Yes.
Do you think with some input repetition we can, like if we repeat the data and we remove some of the irregularities and have like regular access, but instead we still have 7 accesses per computation, do you think we can still see some improvements?
So the question is, even though you're eliminating some accesses, you still need to do the computation for the data, right? So the question is whether or not you can have further improvement. The answer is depends. In some computation, especially I think in this one is probably okay, because the way that you can actually do it is not to fetch a new method, a new value, and then do the computation again. You can just take the value, and then you can subtract the effect of the one that you're leaving out of the window, and then you just add the effect of the value into your sum, right? But that requires the coefficient of all the values to be the same. If the coefficient values are different in some of the higher order values, then they will not work. But for this particular case, it should work. In fact, you should try it in your MP. Okay. Good point. Any other? So that trick is actually used in a lot of the image, image computation, because image computation are filters, right? The filters are actually stencil. So the way that the energy efficient calculation of image, image processing is exactly this. When they move from one pixel to the next pixel, when they do the computation, they just take away some effect and then add some effect rather than recalculating the whole thing. Okay. Very good observation. Now, so the in and out arrays are let's kind of do a little bit additional thing, because a few issues with that are unique with the stencil code that you need to understand in order to be able to really understand how to write stencil code. So one of the problems with stencil code is that, remember, when we calculate each grid point, we need to have the surrounding values, right? Whenever you hear this, you should start to, immediately there should be an alarm. What happens when the point is at the edge, right? So if you're on the left edge, you don't have a left neighbor to work with, right? So these are what we call the ghost cells, or the halo cells, and so on. So we assume that for the data structure, we pattern with one extra slice of 0 elements for each n, in the x, y, and z dimensions to simplify your code. Okay, but in reality, a lot of times there will not be padding, so you need to do all the condition checking in order to make it work. So I'm going to show you some condition checking code just to so that you understand the complexity in practice. Okay, so the nx, ny, and z are dimensions of the array supplied to the kernel reflects the padded elements. So this makes your code a lot easier to write. But in practice, you will most likely need to be able to process non-padded input data. So when we look at the kind of the coarsened kernel code, we're going to map our the block index and thread index of our code of our threads into the I and j index of the output element, right? So we have this I and j, so essentially we're identifying the I and j of that pencil, and then you're going to go up in the z dimension, right? So we predetermine the I and j, and then we will increase z as we go. So for each thread, we have the I and j, right? We have the I and j. So now we load 0, 1, and 2 for element 1. Remember that 0 is the padded element, right? So we're not going to calculate that 0. But we take advantage of padding so that we just access 0, 1, 2 for calculating 1, right? Element 1. Okay? So we load those 3 for the thread. In reality, when you look at the thread block, everyone is loading 3 elements, right? So you're loading 3 small rectangular slices, right? From the thread block point of view. Okay, now. So then we go up in the z direction. We start with 1, and then we end with nz minus 2, right? Because the top one also is a padded one, right? So then we go, as we go up, we do some testing, and make sure that I is greater than 0, and so essentially we only calculate the meaningful grid indices, right? So we screen out I equal to 0, that's padded, right? And I equal to nx, that's also padded, right? So j the same thing, right? J the same one. So if we pass the test, that means that the thread falls within the kind of the valid original data range, right? For the grid. So then we do the calculation. We take the bottom one, right? The bottom value, the top value, right? The bottom and top values. And then, we take the 4 values. We take the 4 values from the global memory, right? Because we don't have them in the registers, okay? So we fetch them from the global memory. And I'm going to come back to this point, okay? There's one more level of optimization. But as far as the register tiling is concerned, we have the top and bottom in the registers, but we don't have these horizontal neighbors in the register. So we go to the global memory to fetch these 4 values. And the current is also in the register, right? So we do the -6 and +1 coefficient. We calculate the output, right? We calculate the output. And then once we finish the current output point, we make the current into the next bottom, right? We are going up. So the current value becomes the bottom for the next higher grid point. And the top becomes the current of that next point. And we need to fetch a new top, right? So this is the additional element we're going to need to fetch for the next one, right? So then we go back. We go back and calculate the next one. And then we go and go and go. So this is traversal. Okay, this is what we call traversal in the z dimension. We go one element each time, and then eventually we finish the entire pencil in the z direction for that thread. So this is the code where we only do on average 5 memory accesses for the original 7 input elements. Right? Now we can further optimize this, because remember we're fetching the horizontal surrounding elements from the global memory, right? But what are these surrounding elements? The surrounding elements are actually the current element of your neighbors, right? You're fetching something to your right, but that's actually the current element for calculating the next value of your right. So your neighbor already has that value. It's just that you cannot get your hands on it. They're in the register, right? They're in your neighbor's register, so you cannot get your hands on it. So this is the reason why I bothered to talk about the fact that registers are private, right? So when you do the register tiling, you can only benefit within the thread. You cannot benefit across the threads. So, but we have the shared memory. Okay, we have the shared memory where if you put the data into the shared memory, your neighbor's threads can see it, right? So if we systematically put the current value of all these threads into the shared memory, then everyone can just reach to the left, to the right, and fetch them from the shared memory, and therefore they no longer need to access the global memory for those values, right? So we have a few things to worry about. When we start to think about our neighbors, then you need to begin to think about the edge, right? The edge elements, in the y dimension, and the edge elements in the x dimension, right? Edge elements in the x dimension. So for these cases, you need to be able to to have the special case in terms of how you're going to calculate it. So if you pad it, then the concern goes away, right? But if you don't pad it, then you need to deal with that complexity. So I'm going to show you some complexity if you didn't, have it. So this is what we call the 2D shared memory tiling for a 3D stencil. Okay, the reason is we already took care of the Z dimensions through register tiling. So when we tile data in the horizontal direction, to eliminate more accesses in that horizontal direction, we only need to have two-dimensional tiling, just so that every thread can reach into the neighbors and get the horizontal neighbors, right, in the X and Y dimension. So we assume that all the threads of a block march up in the Z dimension, and then we will synchronize them. Okay, in this case, we need to synchronize them. We need to make sure that all the threads are traversing up at exactly the same pace. So when we have a step, all the current values, okay, all the current values in each thread's register, all the current values correspond to exactly the same horizontal plane. No threads can go ahead of others. You said, why would they? Of course they can, because these thread blocks are going to be broken into warps. Okay? If you don't synchronize them, threads from different warps can actually get ahead or behind each other. So then if you have a poor thread is at the end of that warp, reaching to the right, it may be reaching to the wrong value. Okay? So that's why you need to have that synchronization to make sure that all the threads in a block, no matter which warp they belong to, will be at exactly the same point of the horizontal, in terms of their horizontal plane, right? Okay, so in each phase, all the threads calculate a two-dimensional slice of the rectangular output element. So, all the threads are going to go up one level and calculate the output value for every grid point in that horizontal plane. And then they move up to the next one, okay? So for each phase, we maintain 3 slices of the relevant input in the on-chip memories, okay? How do we do that? We already talked about the first part. Every thread is going to have that top, current, and bottom in their registers, right? In the registers. So we already have those 3 layers in all the threads, okay? In all the threads. Remember, the problem is they cannot reach into each other's registers. The solution is also store the current value into the register, or into the shared memory, right? Into the shared memory, so that everyone can reach to the side, right? And fetch them from the register, from the shared memory. Now, so that's why one top, one current, and one bottom element each, so that's private registers, but then all the current elements need to be also in the shared memory. And now suddenly, when you calculate that element, you can fetch the top and bottom from your registers, and then you fetch the 4 surrounding neighbors from the shared memory, right? And then you no longer need to access global memory for it. So this is how it works. I start, I still start with the top, bottom, and current, right? So that the code is still there. But then I will move my current, from the register. I'll copy my current value into the shared memory, okay? Indexed by the thread XY, right? The XY of my thread index, right? So, now I created a shared memory array where the XY gives me the exact location in that slice, right? Okay. So now I sync threads and make sure that all the threads are going to be, walking up in sync with each other. And we still need to do all this testing, okay? And so that we may have a situation where, look at this. We're calculating this part, so I can reach to the right, I can reach to the left, and so on. But if I'm at the edge of my tile, right, of my thread block, this guy could not be found in the shared memory, right? Unless I actually load them into the shared memory. So this tells me that, I can do the test and then, only load from the shared memory if I'm within the range, but if it's greater than 0, I can just go to global memory, right? So I will have a little bit of overhead, right? This is the reason why you never get the perfect benefit in real systems, okay? These are the details that will shave away your benefit, okay? And you need to understand where these things come from and how you're going to lose some of these the benefits. So I need to do the test, and then in some cases I still need to go to the global memory to fetch it. But hopefully, if the block size is reasonably big, you don't go to the global memory very often. Okay. Now, so this is I go into the for each iteration, I test whether or not I'm at the edge of my tile or the thread block, or in the middle of the thread block, okay? Whenever I'm in the middle of the thread block, I can access the shared memory for all my neighbors. But if I'm at the edge, in either X or Y, I will end up accessing the global memory, right? So this, gives me the calculation of the horizontal, the input of the horizontal neighbors. And then I do a sync thread, and I do the bottom, current, and top, right? Just like what I had before. However, I need to, I need to make sure that the current top, right? The current top, which is the what? The next iteration's current, right? The top element of the current iteration goes into the shared memory, and it also goes into the current for the next iteration, and that gives me the next 2D tile for all the threads, and then I still need to fetch one more element from the global memory, right, for the next grid point. Okay, so this gives me the code. I'm almost there. So there are a few things that in our typical exams, I'm going to ask you to analyze. So for one phase to the next, the kernel code moves the current element from the current register to the bottom register, moves the top element from the top register to the current register and shared memory, and load the new top element from the global memory to the register. And we need to deal with halo data. In the code that I gave you, we assume that whenever you are at the edge, you go to global memory, right? You can also try to load those halo elements from the global memory into the shared memory. You could try to do that. But the benefit is very limited. In fact, it's probably better if you didn't. Because remember, the benefit for shared memory is that you reuse the data. But if you're at the edge, only one thread will use it. So you're not reusing the data anyway. Right. So you may as well, but you reduce the divergence when you do the calculation. You reduce the need for testing if you pad it, if you actually load it. But the problem is you introduce divergence during the loading phase. So we're not solving any problems here. We're just pushing the problem around. Okay. And so you decide where the pain is. Okay. The pain is not going to go away. And you move it around until it's less painful, okay? So someone says, I'm going to punch you, okay? You said, okay, can I choose where I get punched? That's really what it is, okay? In some cases, it actually helps. If I have to choose between a punch in the face versus a punch maybe in the butt, the choice is pretty clear, right? So, but in some cases, the choice may not be that clear, okay? So, you make your choice wisely, right? And so, for each of the 2D, the tile, if we try to, load all the halo elements into the shared memory, we actually can increase the number of elements that we load significantly. Okay, it's quite significantly. So let's say, if we have a somewhat smaller tile of 16 times 8, 128 threads, in our kind of column, and then each slice calculates 128 8 elements, the 128 output elements as we go up. So if we want to also load all the halo elements, right, on the in the x dimension and the y dimension, we add 2 more elements in each dimension, right? Each end, and 2 more elements. Oftentimes when you calculate these numbers, you start to see some very sobering phenomena. You almost add 50% loads into that, even though you think that, oh, I'm only adding 1 more element on each side, because of the multiplicative effect of area. Essentially, we're increasing the area, right? So you can actually have very significant increase in terms of the number of elements you add. So, for example, when you order pizza, okay, when you order pizza, you say, I'm going to order something like an 8-inch, okay, versus a 12-inch, right? You said, how much more should a 12-inch pizza be compared to an 8-inch pizza? And if the pizza is actually area, right? So 12-inch pizza is 144 in area, right? And the 8-inch is 64. So the 12-inch pizza should be more than double the price of the 8-inch. So if they only give you 50% more price, definitely order 12-inch. Okay. So when I was a grad student, I do that calculation all the time. Okay, and when I became a professor, I do that calculation all the time. Okay, so it's a principle. Okay, you optimize. And I really optimize. When it comes to Papadale, when it comes to any of these pizza stores, they all pay attention. You can always optimize when you order. Okay, so this might be the most valuable advice I give you for this course. Okay, so in a Coarsen register power code, each output element needs 5 loads from the global memory. Okay, so if we didn't use the shared memory, then we need to load 128 elements, right? And then if we didn't do the shared memory for each element, we're going to need to load 5, right? The self and then the surrounding 4. So the total ratio of improvement for the shared memory calling should be 640 divided by 174. This is after loading the halo elements. So this is 3.6. But so if we have a perfect optimization, we should be able to eliminate all the elements. So everyone just only load once into the machine. So it should be 5 times. But then because of all these boundary conditions and so on, we often end up with something much smaller than what we expected. Okay. So the value of N and M are limited by the amount of registers, because N and M is determined by the total number of elements you can accommodate, right, with each thread block, and they are mapped into the streaming multiprocessor. Okay. So, I already talked about this. So, when you calculate all the, global memories that you can really eliminate in the condition code, you get 3.6. But then you could try to load all the halo elements into the shared memory, but then the elements that you load into the shared memory don't get reused. So if you calculate the real reuse, it's not going to be that different. Okay? And we actually have done something similar in the convolution exercise in 408. Okay, so if you don't remember, go back and take a look at it, right? Because these things are, you're going to have to do this kind of calculation quite often in practice. So, in the recent GPUs, this is about the hardware trend. It's actually better not to load the halo elements into the shared memory. The reason is the halo cells are most likely already loaded by the neighboring thread blocks. Remember, these are the elements that are really being computed by your neighboring blocks, right? They're not in your shared memory naturally. However, these halo cells are already often available in the L2 cache because your neighboring thread blocks will be probably executing close to you. So the fact that they loaded them into their registers means that the data will likely be in the L2 cache. So when you try to load it from the global memory, oftentimes the data is already in the L2 cache, and you don't really need to go all the way to DRAM to cache them anyway. So for the more recent GPUs, the cost of doing that conditional branch and then fetch it from the global memory is actually quite minimal. Yes?
Wouldn't that really depend on the size of the problem as well as
Yes.
the scheduling policy or whatever the hardware?
It's actually depending on the ratio of the compute unit versus the L2 capacity. If you think about it. Yeah, it's actually independent of problem size. Because you only have a window of your problem, right?
Oh, right.
Okay. So we ran over 5 minutes, right? But this should give you everything you need in order to do the next MP. So we just went through the second simplest technique that we're going to be using this semester. Okay, the simplest technique is that scatter together transformation, and you're going to be using that again and again in your career. The second simplest one is this transformation of granularity of your threads so that you can play some of these tricks, right? And these tricks are very dependent on the hardware in terms of the benefit, but they are actually independent in terms of the desire to use these techniques. If you look at NPI programming, if you look at OpenMP programming, they all use these techniques extensively. So any additional questions? If not, finish MP1 by Thursday and start MP2. Okay? So I'll see you on Thursday.
Hey.